Welcome to the lesson on the geometrical meaning of the zeros of a polynomial. At the end of this lesson, you will be able to define a polynomial and its basic terminology. You will also be able to identify the zeros of a polynomial by plotting it on a graph. Consider the expression 5x cubed minus 2x squared minus x plus 2. This expression is called a polynomial. A polynomial is an algebraic expression consisting of multiple terms. The terms of a polynomial can be variables or variables raised to a power of a whole number, a constant, or the product of these two. The real number that precedes the variable is called the coefficient. For example, in this polynomial, 5, 2, and 1 are the coefficients. In this polynomial, there is only one variable, x. Such a polynomial is called a polynomial in one variable. If x is the variable in a polynomial, then the polynomial is denoted by f of x, p of x, q of x, and so on. The highest part of the variable of a polynomial is called the degree of the polynomial. Based on its degree, a polynomial can be called as linear polynomial, quadratic polynomial, cubic polynomial, and so on. Since the highest degree of this polynomial is 3, this is a cubic polynomial. The general form of a cubic polynomial is ax cubed plus bx squared plus cx plus d, where a, b, c, and d are real numbers, and a is not equal to 0. Here's a second example. As the highest degree of this polynomial is 1, it is a linear polynomial. This is read as p of x is equal to 4x plus 8. The general form of a linear polynomial is ax plus b, where a and b are real numbers and a is not equal to 0. Consider the third polynomial, x squared minus 4x plus 3. Here the highest degree is 2. Such a polynomial is called a quadratic polynomial. The general form of a quadratic polynomial is ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. Now that we have reviewed the definition of a polynomial, let's move on to define the zero of a polynomial. Consider the quadratic polynomial x squared minus 4x plus 3. Let's substitute the value of x as 1 in the polynomial and simplify it. We get the value of the polynomial as 0. This implies that p of 1 is equal to 0. Here the value 0 is the value of the polynomial when the value of x is equal to 1. Now, let's substitute the value of x as minus 1. On simplifying, we get the value of the polynomial as 8. This implies that p of minus 1 is equal to 8. Here the value 8 is called the value of the polynomial when x is equal to minus 1. In general, the value of a polynomial p of x when x is equal to k is the value obtained by substituting x as k. Here k is a real number and the value of the polynomial is denoted by p of k. Now in the first case, the value of the polynomial is 0 when the value of x is 1, which is the value of x, and it is called the zero of the polynomial. The zero of the polynomial is defined as any real value of x, for which the value of the polynomial becomes 0. In general, a real number k is a zero of a polynomial p of x if p of k is equal to 0. Let's discuss the geometrical meaning of the zeros of a polynomial. Here, we will see the graphical representation of a polynomial. Consider the linear polynomial 4x plus 8. Assume that the polynomial is equal to y. To determine the geometrical meaning of the zeros of this polynomial, we'll have to plot this equation on the graph. You must first determine the points representing the x and the y coordinates. For this, we'll assume a few values for x. Substituting these values of x in the equation and simplifying it will give us the values of y. This table gives the x coordinates and the corresponding y coordinates. The x coordinate and the corresponding y coordinate together form an ordered pair that represents a point. Let's locate these points on the graph. On joining all these points, we get a straight line. As you can see, this line intersects the x-axis at the point -2, 0. This means that the line intersects the x-axis when x is equal to -2. As per the definition of the zero of a polynomial, the zero of this linear polynomial is -8 upon 4. This implies that the zero of this polynomial is -2. Based on these observations, we can conclude that the x-coordinate of the point where the graph intersects the x-axis is the zero of the polynomial. In general, if a polynomial p of x intersects the x-axis at k, 0, then we can say that k is the zero of the polynomial. In other words, p of k is equal to 0. The graph of a linear polynomial intersects the x-axis at a maximum of 1 point. Therefore, a linear polynomial has a maximum of 1, 0. Similarly, we can plot the graphs for quadratic and cubic polynomials. We can also find the zeros of these polynomials by identifying the points where the graphs of the polynomials intersect the x-axis. Let's summarize the observations from the graphs. The graph of a quadratic polynomial intersects the x-axis at a maximum of 2 points. Therefore, a quadratic polynomial can have a maximum of 2 zeros, 1, 2, or no zeros. In case of a quadratic polynomial, the shape of the graph is a parabola. The shape of the parabola of a quadratic polynomial depends on the coefficient of x square. If a is greater than 0, then the parabola opens upwards. If a is less than 0, then the parabola opens downwards. The graph of a cubic polynomial intersects the x-axis at a maximum of 3 points. Therefore, it has maximum of 3 zeros. That is, it can have 1, 2, 3, or no zeros. In general, an nth degree polynomial intersects the x-axis at a maximum of n points. Therefore, an nth degree polynomial has a maximum of n zeros. You have reached the end of this section. Before moving on to the next section, let's recap the key points. The x-coordinate of the point where the graph of a polynomial intersects the x-axis is called the zero of the polynomial. An nth degree polynomial intersects the x-axis at a maximum of n points, and therefore has a maximum of n zeros. The graph of a quadratic polynomial is a parabola. The shape of a parabola of a quadratic polynomial depends on the coefficient of x square. If a is greater than 0, then the graph is a parabola that opens upwards. If a is less than 0, then the graph is a parabola that opens downwards. Hope you enjoyed this learning experience. Welcome to the lesson on the relationship between zeros and coefficients of a polynomial. At the end of this lesson, you will be able to establish the relationship between the zeros and the coefficients of linear polynomials, quadratic polynomials, and cubic polynomials. Let's consider a linear polynomial 2x plus 5. Here x is the variable with 2 as its coefficient and 5 is the constant term. Now, let's find the zero of this polynomial. The zero of a polynomial is defined as any real number k, for which the value of the polynomial becomes 0. Let's assume that for x equal to alpha, the value of p of x becomes 0. Thus, p of alpha is equal to 0. This implies that 2 alpha plus 5 is equal to 0. On simplification, we get the value of alpha as minus 5 divided by 2. Here you observe that the numerator 5 is the constant term of the polynomial, and the denominator 2 is the coefficient of the variable x. Based on this observation, we can conclude that the zero of a linear polynomial is equal to the minus of the constant term divided by the coefficient of x. Now, let's consider the general form of the linear polynomial p of x is equal to ax plus b, where a is not equal to 0. Recall that a linear polynomial can have a maximum of one zero. Let's assume that alpha is the zero of the linear polynomial ax plus b. Hence, we can say that p of alpha is equal to 0. This implies that a multiplied by alpha plus b is equal to 0. On simplifying this expression, we get alpha is equal to minus b divided by a. Here b is the constant term and a is the coefficient of the variable x of the linear polynomial. This equation defines the relationship between the zero and the coefficient of the linear polynomial. Next, we'll discuss the relationship between the zeros of quadratic and cubic polynomials with its coefficients. Let's consider the general form of the quadratic polynomial. Recall that a quadratic polynomial can have a maximum of two zeros. Let's assume that the zeros of the polynomial p of x are alpha and beta. Here we will apply the factor theorem to determine the factors of p of x. Recall that the factor theorem states that if a is a zero of a polynomial p of x, then x minus a is a factor of p of x. In case of a quadratic polynomial, if alpha and beta are zeros of the polynomial p of x, then the factors of p of x are x minus alpha and x minus beta. Thus, the quadratic polynomial is equal to k multiplied by x minus alpha multiplied by x minus beta, where k is a constant not equal to 0. Let's multiply the factors on the right-hand side of the equation. The equation obtained is as shown. Now, let's compare the coefficients on both the sides of the equation. A is equal to k. This is by comparing the coefficient of x square. Let this be equation 1. B is equal to minus k multiplied by alpha plus beta. This is by comparing the coefficient of x. Let this be equation 2. and c is equal to k multiplied by alpha multiplied by beta. Let this be equation 3. Now, let us use the equation 1 and equation 2 to get this relation. This equation indicates that the sum of the zeros is equal to minus b divided by a. Here b is the coefficient of x and a is the coefficient of x square. Therefore, this equation establishes the relationship between the sum of zeros and coefficients of the quadratic polynomial. On using equation 1 and equation 3, we get the product of zeros, which is equal to c divided by a. Here c is the constant term and a is the coefficient of x square. Therefore, this equation defines the relationship between the product of zeros and the coefficients of a quadratic polynomial. Next, let's consider the general form of the cubic polynomial. Let's assume the zeros of a cubic polynomial p of x are alpha, beta, and gamma. Based on the factor theorem, if alpha, beta, and gamma are zeros of p of x, then the factors of p of x are x minus alpha, x minus beta, and x minus gamma. As we have seen in the quadratic polynomial, the cubic polynomial is equal to the product of its factors. Let's simplify and rearrange the right-hand side of the equation. Now, we'll compare the coefficients of x, x square, x cube, and the constant term. A is equal to k. Let this be equation 1. B is equal to minus k into the sum of zeros, alpha, beta, and gamma. Let this be equation 2. C is equal to k into the sum of the product of zeros taken 2 at a time. Let this be equation 3. D is equal to minus k into the product of the zeros. Let this be equation 4. Using equation 1 and 2, we get the sum of zeros is equal to minus b divided by a. Here b is the coefficient of x square and a is the coefficient of x cube. Therefore, this equation defines the relationship between the sum of zeros and the coefficients of the cubic polynomial. Next, by using equation 1 and 3, we get the sum of the product of zeros taken 2 at a time is equal to c divided by a. Here c is the coefficient of x and a is the coefficient of x cube. Therefore, this equation defines the relationship between the sum of the product of zeros taken 2 at a time and the coefficients of the cubic polynomial. Similarly, using equation 1 and 4, the product of zeros is equal to minus d divided by a. Here d is the constant term and a is the coefficient of x cube. Therefore, this equation establishes the relationship between the product of zeros and the coefficients of the cubic polynomial. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. The zero of a linear polynomial is equal to the minus of its constant term divided by the coefficient of x. If alpha and beta are the two zeros of a quadratic polynomial, then the sum of the zeros of a quadratic polynomial is equal to the minus of the coefficient of x divided by the coefficient of x squared. And the product of the zeros of a quadratic polynomial is equal to the constant term divided by the coefficient of x squared. If alpha, beta and gamma are the three zeros of a cubic polynomial, then the sum of the zeros of a cubic polynomial is equal to the minus of the coefficient of x squared divided by the coefficient of x cubed. The sum of the product of zeros taken two at a time of a cubic polynomial is equal to the coefficient of x divided by the coefficient of x cubed. And the product of the zeros of a cubic polynomial is equal to the minus of a constant term divided by the coefficient of x cubed. Hope you enjoyed this learning experience. Welcome to the lesson on the division algorithm for polynomials. At the end of this lesson, you will be able to divide one polynomial by another polynomial. You will also be able to state and verify the division algorithm for polynomials. Let's perform a simple division of 36 by 5. Notice that the quotient is 7 and remainder is 1. We can recall Euclid's division algorithm here. That is, the dividend is equal to the divisor into the quotient plus the remainder. In this case, 36 is equal to 5 into 7 plus 1. Suppose we have polynomials as the dividend and divisor. To perform the division, first we arrange the terms of dividend and divisor in decreasing order of their degrees. Thus, the dividend becomes x cubed minus 6x squared plus 12x minus 8. Let's perform the division. First, we'll divide the first term of the dividend, x cubed, by the first term of the divisor, x squared. We get x. This is the first term of the quotient. We multiply the divisor with the first term of the quotient and subtract this product from the dividend. That is, we multiply x squared minus 3x plus 2 with x and subtract the product x cubed minus 3x squared plus 2x from the dividend. The remainder is minus 3x squared plus 10x minus 8. Now, this remainder is our new dividend. The divisor is the same. To get the second term of the quotient, divide the first term minus 3x squared of the new dividend by the first term x squared of the divisor. So we get minus 3 as the second term of the quotient. Multiplying the divisor with the second term of the quotient and subtracting the product minus 3x squared plus 9x minus 6 from the dividend gives x minus 2 as the remainder. Now, x minus 2 is our new dividend and the divisor is x squared minus 3x plus 2. Can you perform further division? Let's see. In order to get the third term of the quotient, we divide the first term, x of the new dividend, by the first term of the divisor, x squared. On division, we get 1 divided by x, which is not a polynomial. Thus, this cannot be the third term of the quotient. Therefore, further division is not possible. Here the degree of the remainder, x minus 2, is 1, but the degree of the divisor is 2. This implies that division is not possible if the degree of the remainder is less than the degree of the divisor. In general, the division algorithm for polynomials states that if f of x and g of x are the polynomials such that the degree of f of x is greater than or equal to the degree of g of x where g of x is not equal to 0, then there exists unique polynomials q of x and r of x such that f of x is equal to g of x into q of x plus r of x, where r of x is equal to 0 or the degree of r of x is less than the degree of g of x. This is known as the division algorithm for polynomials. Let's now verify the division algorithm for a polynomial division just performed. Here you have divided x cubed minus 6x square plus 12x minus 8 by x square minus 3x plus 2. On performing the division, the quotient is x minus 3 and the remainder is x minus 2. Now, we'll substitute the values of the divisor, the quotient and the remainder in the algorithm. Let's simplify this. We get x cubed minus 6x square plus 12x minus 8. This is the dividend that we have taken. Hence, we have verified that the division algorithm holds true for polynomial divisions. You have reached the end of this section. Let's recap the division algorithm for polynomials, which states that if f of x and g of x are the polynomials such that the degree of f of x is greater than or equal to the degree of g of x, where g of x is not equal to 0, then there exists unique polynomials q of x and r of x such that f of x is equal to g of x into q of x plus r of x, where r of x is equal to 0 or the degree of r of x is less than the degree of g of x. Hope you enjoyed this learning experience.